A sequence of powerful seismic events has unfolded across the Southwest Pacific, concentrating attention on a region already known for some of the most complex tectonic interactions on Earth. Within a span of less than one full day, 4 significant earthquakes struck near Tonga and adjacent areas, raising immediate questions about clustering behavior, stress transfer within the subducting slab, and whether this sequence represents a transient burst of activity or part of a broader escalation. The timing, depth variation, and spatial distribution of these events introduce a pattern that is difficult to dismiss as isolated coincidence. Why did multiple strong earthquakes occur so closely together in both time and space? What mechanisms within the Earth's interior could allow stress to accumulate and release in such rapid succession? And how does this latest sequence compare to decades of seismic history in the Tonga region? The largest event in this sequence registered a magnitude 7.5 and occurred roughly 166 kilometers west of Neiafu. Its origin time was recorded at 4 hours, 37 minutes and 50 seconds Coordinated Universal Time on March 24, 2026. The hypocentral depth was approximately 229.5 kilometers, placing it firmly within the category of intermediate depth earthquakes. The geographic coordinates near 18.668 degrees south latitude and 175.560 degrees west longitude situate the rupture within the descending Pacific plate, well below the surface interface where most tectonic plate boundaries are commonly observed. This event did not occur in isolation. In the hours leading up to it, 3 additional earthquakes exceeding magnitude 6 were recorded in nearby regions. One measured magnitude 6.3 and occurred about 144 kilometers northeast of Hihifo at a depth of 10 kilometers. Another, magnitude 6.2, struck roughly 102 kilometers northeast of Hihifo, also at a shallow depth of 10 kilometers. A third earthquake, also magnitude 6.2, occurred approximately 149 kilometers southwest of Lotofega, Samoa, again at a depth of 10 kilometers. These 3 shallower earthquakes preceded the deeper and more powerful magnitude 7.5 event, forming a compact temporal cluster that spans less than 24 hours. The contrast in depth between these earthquakes is critical to understanding their origin. The shallower events occurred near the upper portion of the tectonic system, likely within or near the interface region, or upper crustal structures influenced by plate convergence. In contrast, the magnitude 7.5 earthquake originated far deeper, within the interior of the subducting Pacific plate itself. This distinction indicates that the sequence is not confined to a single structural level, but instead reflects activity occurring across multiple layers of the subduction system. The Tonga region sits along one of the most active convergent plate boundaries in the world, where the Pacific plate is forced westward beneath the Australia plate. This process, known as subduction, generates intense deformation as the descending slab bends, fractures, and interacts with surrounding mantle material. Over time, stress accumulates within the slab due to a combination of compressional forces near the trench and extensional forces as the plate bends and sinks deeper into the mantle. The deeper earthquake in this sequence is consistent with normal faulting, a mechanism that reflects extension rather than compression. This occurs because the slab, as it descends, experiences internal stretching, particularly at intermediate depths. Focal mechanism solutions for the magnitude 7.5 earthquake indicate rupture along either a shallowly dipping fault striking toward the southwest or a steeply dipping fault oriented toward the northeast. Both interpretations are consistent with extensional stress within the slab. The moment tensor solution shows a dominant double couple component, accounting for approximately 87% of the seismic energy release. This suggests a relatively clean rupture process, without significant complexity from volcanic or non-tectonic influences. The rupture itself likely extended across a fault plane, measuring approximately 70 kilometers in length and 30 kilometers in width. This scale is typical for earthquakes of this magnitude occurring at intermediate depths. Unlike shallow earthquakes, which often produce intense ground shaking directly above the rupture zone, intermediate depth earthquakes tend to distribute their energy over a broader area. As a result, they are frequently felt across large distances, sometimes spanning hundreds or even thousands of kilometers, while producing comparatively less severe damage at the surface directly above the hypercenter. Despite this general pattern, the depth does not eliminate the significance of the event. The energy released by a magnitude 7.5 earthquake is substantial, and when combined with preceding events, it raises the question of whether stress redistribution within the slab is occurring rapidly enough to trigger successive ruptures. The earlier magnitude 6 events, though smaller, may have altered stress conditions either locally or regionally. While they occurred at much shallower depths, the interconnected nature of tectonic systems means that stress changes can propagate through the crust and into deeper structures. Historical context adds another layer to this sequence. Since the year 1950, at least 6 earthquakes of magnitude 7 or greater have occurred within a radius of approximately 250 kilometers from the location of the latest magnitude 7.5 event. The most recent prior event of similar scale occurred in March 2025, registering magnitude 7. The largest recorded in this cluster was a magnitude 8 earthquake on May 3, 2006, which caused only minor damage despite its size. This historical pattern suggests that while large earthquakes are not uncommon in the region, the clustering of multiple magnitude 6 and greater events within such a short time frame remains noteworthy. The timing of the events on March 22 is particularly striking. 2 of the magnitude 6.2 earthquakes occurred within minutes of each other, with origin times separated by only a few minutes. This near simultaneity raises the possibility of dynamic triggering, where seismic waves from one earthquake influence the stress state of nearby faults, potentially initiating additional ruptures. The presence of another magnitude 6.3 earthquake within the same day further reinforces the impression of an active and rapidly evolving seismic sequence. The deeper magnitude 7.5 earthquake on March 24 may represent a continuation of this process, though occurring within a different structural domain. Its depth places it within the portion of the slab that experiences different physical conditions, including higher pressure and temperature compared to the shallow crust. At these depths, rocks behave differently, and the mechanisms that allow brittle failure and earthquake generation are still subjects of ongoing research. The occurrence of a large normal faulting event at this depth indicates that the slab retains sufficient rigidity to accumulate and release stress in a manner similar to shallower regions. The principal axes of the earthquake stress field further clarify the nature of the deformation. The axis representing maximum extension aligns with the direction expected from slab pull forces, where the weight of the descending plate exerts a downward and outward pull. This alignment supports the interpretation that the earthquake was driven by internal stresses within the slab rather than by direct interaction at the plate boundary interface. The geographic distribution of the earthquakes also deserves attention. The shallower events near Hihifo and the Samoa region are separated by distances exceeding 100 kilometers, yet they fall within the broader zone of tectonic interaction associated with the Tonga Trench. This suggests that the entire region is experiencing elevated stress conditions rather than a single localized fault system being activated. The deeper event west of Neafu extends this pattern further, indicating that the zone of activity spans both horizontally across the region and vertically through different layers of the Earth's lithosphere. In practical terms, the effects of such a sequence depend heavily on local conditions, including population distribution, infrastructure resilience, and the depth and distance of each event relative to inhabited areas. The shallow earthquakes, despite being smaller in magnitude, have a greater potential to produce strong ground shaking locally due to their proximity to the surface. The deeper magnitude 7.5 earthquake, while larger, would distribute its energy over a wider area, potentially being felt across multiple island groups and even beyond the immediate region. The rapid succession of these events within a single day underscores the dynamic nature of subduction zone environments. It also highlights the challenges in interpreting seismic sequences in real time. While each earthquake can be analyzed individually, understanding their relationship to one another requires consideration of stress, transfer, fault interaction, and the evolving state of the tectonic system. The Tonga region, with its steep subduction angle and fast convergence rates, provides a setting where such interactions can occur on relatively short timescales. As seismic monitoring continues, additional data will refine the understanding of this sequence. Aftershocks, if they occur, may help delineate the geometry of the ruptured fault planes and reveal how stress is being redistributed following the main events. The depth distribution of these aftershocks will be particularly important in determining whether the activity remains concentrated within the slab or migrates toward shallower regions. The evolving seismic pattern across the Tonga region in the hours following the initial cluster continues to draw attention to how stress is redistributed through a subducting plate system that is both fast-moving and structurally complex. The presence of a deep magnitude 7.5 earthquake following multiple shallow magnitude 6 range events suggests that stress was not confined to a single fault plane or depth level, but instead involved a broader section of the Pacific plate as it descends beneath the Australia plate. This type of vertical coupling, where activity occurs both near the surface and hundreds of kilometers below, is a defining characteristic of the Tonga subduction zone and helps explain why sequences here can appear both rapid and spatially dispersed. As seismic waves from each event propagate outward, they interact with surrounding faults and fractures, temporarily increasing or decreasing the likelihood of failure depending on how stress is transferred. In this sequence, the proximity in time between the magnitude 6.2 and magnitude 6.3 earthquakes on March 22 indicates that stress changes were occurring almost immediately after each rupture. When earthquakes occur within minutes of each other, it often points to dynamic triggering, where the passing seismic waves themselves influence nearby faults enough to push them past their failure threshold. This mechanism does not require long-term build-up, but instead relies on instantaneous stress perturbations that can cascade across a region. By contrast, the deeper magnitude 7.5 earthquake that followed roughly a day later may reflect a different process. At depths approaching 200 kilometers or more, the physical conditions are markedly different. Temperatures are higher, pressures are immense, and the rock within the slab behaves in ways that are not fully analogous to shallow crustal faulting. Yet despite these conditions, the slab can still fracture in a brittle manner, producing earthquakes of considerable magnitude. This is often attributed to processes such as dehydration embrittlement, where minerals release water under high pressure and temperature, weakening the surrounding rock and allowing sudden slip to occur. The Tonga subduction zone is particularly conducive to such behavior due to its steep angle and rapid convergence rate. The Pacific plate in this region is among the fastest-moving tectonic plates on Earth, descending westward at rates that can exceed several centimeters per year or more than 1 inch annually. As it bends and sinks, it accumulates internal stresses that are eventually released through earthquakes at varying depths. The magnitude 7.5 event aligns with this model, representing a release of extensional stress within the slab as it is pulled downward by its own weight. The geometry of the rupture further reinforces this interpretation, with an estimated fault area of about 70 kilometers in length and 30 kilometers in width. The event reflects a significant portion of the slab undergoing deformation. The normal faulting mechanism indicates that the slab was being stretched rather than compressed, which is consistent with the bending and unbending processes that occur as the plate transitions from the trench into the deeper mantle. This internal deformation is distinct from the mega-thrust earthquakes that occur at the plate interface, which are typically compressional and often associated with the largest and most destructive seismic events. One of the notable aspects of in intermediate depth earthquakes is their ability to be felt over wide regions. Because they occur deep within the earth, the seismic waves they generate travel through more uniform material before reaching the surface, allowing them to propagate efficiently over long distances. Reports from similar past events in the Tonga region have indicated that shaking can be detected across multiple island groups and even on distant land masses, depending on the magnitude and depth. While the intensity of shaking at any given location may be lower than that of a shallow earthquake of similar size, the geographic reach is often far greater. The earlier shallow earthquakes in this sequence, each occurring at depths of about 10 kilometers or roughly 6 miles, present a different set of considerations. Shallow earthquakes tend to produce stronger ground motion near the epicenter because the energy has less distance to travel before reaching the surface. Even though the magnitudes of these events were in the low 6 range, their potential impact on local communities could be more pronounced than that of the deeper magnitude 7.5 event. The combination of shallow and deep earthquakes within such a short period raises the possibility of compounded effects, where infrastructure already stressed by one event may be more vulnerable to subsequent shaking. Another factor to consider is the spatial relationship between the events. The earthquakes near Hihifo and those south-southwest of Lotofaga, Samoa, are separated by distances on the order of 100 to 150 kilometers, or roughly 60 to 90 miles. While this may seem significant, in tectonic terms it falls well within the network of influence for stress transfer, especially in a region where the plate boundary itself extends for thousands of kilometers. The deeper event west of Nyafu, located approximately 166 kilometers or about 103 miles from that reference point, adds another dimension to the pattern, suggesting that the activity spans a broad section of the subduction system. Historical seismicity in the region provides additional context for interpreting this sequence. The record of at least 6 magnitude 7 or larger earthquakes within a 250-kilometer radius since the mid-20th century indicates that the Tonga region is capable of producing large earthquakes at relatively regular intervals. However, the clustering of multiple magnitude 6 and greater events within less than a day is less common and warrants closer examination. It raises the question of whether the region is experiencing a temporary surge in activity or whether this sequence is part of a longer-term pattern that has yet to fully emerge. In previous sequences observed in subduction zones around the world, clusters of earthquakes have sometimes preceded larger events, while in other cases they have represented the primary release of accumulated stress. Distinguishing between these scenarios in real time is challenging, as it requires not only detailed seismic data, but also an understanding of the evolving stress field within the Earth's crust and mantle. In the Tonga case, the presence of a magnitude 7.5 earthquake following the initial cluster suggests that a significant portion of stress has already been released, but it does not preclude the possibility of further activity. Monitoring efforts in the aftermath of these events will focus on detecting aftershocks and any additional large earthquakes that may occur. Aftershocks are typically smaller than the main event and occur as the crust and slab adjust to the new stress distribution. Their spatial distribution can help map the extent of the rupture zone and provide insight into which areas have experienced the greatest changes in stress. In the case of an intermediate depth earthquake, aftershocks may occur at similar depths, though they can also extend into adjacent regions of the slab. The role of seismic networks in capturing this data is critical. Modern instruments are capable of detecting even small earthquakes, allowing scientists to build a detailed picture of how the sequence evolves over time. This information is not only valuable for understanding the current events, but also for improving models of seismic hazard in the region. The Tonga subduction zone, with its high level of activity, serves as a natural laboratory for studying the processes that govern earthquake generation at both shallow and deep levels. The broader implications of this sequence extend beyond the immediate region. Subduction zones around the world share many common features, and insights gained from one area can often be applied to others. The interaction between shallow and deep seismicity, the role of dynamic triggering, and the mechanisms of intermediate depth earthquakes are all topics of ongoing research. Each new sequence provides additional data that can refine existing models and improve the ability to anticipate how similar events might unfold elsewhere. At the same time, the unpredictability of earthquake sequences remains a fundamental challenge. While patterns can be identified and probabilities estimated, the exact timing, location, and magnitude of future earthquakes cannot be determined with precision. This uncertainty underscores the importance of preparedness and resilient infrastructure, particularly in regions that are known to be seismically active. For island communities in the Southwest Pacific, where distances between population centers can be vast and resources may be limited, the ability to respond effectively to seismic events is especially important. The events of March 22 through March 24 illustrate how quickly conditions can change in a tectonically active region. Within a single day, multiple faults at different depths were activated, releasing energy that had been accumulating over extended periods. The sequence highlights the interconnected nature of the Earth's interior, where processes occurring hundreds of kilometers below the surface can be linked to activity much closer to the crust. As the situation continues to develop, attention will remain focused on whether additional significant earthquakes occur and how the region responds to the stress changes introduced by this sequence. Each new data point will contribute to a clearer understanding of the mechanisms at work, but the complexity of the system ensures that many questions will remain. If you found this detailed breakdown informative and valuable, make sure to like, share, and subscribe for more in-depth coverage of major global events. Tap that hype icon to help this reach a wider audience and keep more people informed about what is happening beneath the surface of our planet.